Well, hi there, boys and girls. We're going to do a couple more examples of some related rates questions, so let's just go ahead and get started. I've got two vehicles approaching an intersection. I've got a truck from the west going 15 meters per second. Got a van from the north at 20 meters per second. We want to know how fast is the distance between the vehicles changing when the instant the truck is 60 meters west and the van is 80 meters north. So we're still going to go through our checklist. We're going to draw a picture in motion. So let's go do that real quick. So here's going to be our picture in motion. Okay, so I've got a van coming from, this is a truck coming from the west. So here's our truck coming from the west. And here's our van, get that, get it? Our van coming from the north. So there's our picture in motion. This is coming from the west, this is coming from the north. We can see that that distance between them, the distance currently is we better not do that color. We better do that color, right, Kelsey? The distance currently is whatever that distance is, we'll call that D. But as we move these closer from the west and from the north, we can see that that distance actually gets shorter. So our distance is decreasing. So there's our picture in motion. Let's come up with the equation that relates all of these variables together. I've got an x component from the west, a y component from the north, and a d distance. And this is obviously going to be a Pythagorean Theorem relationship. X squared plus y squared is equal to d squared. So now that we've done our picture in motion and we've got our equation, the next thing we want to do is to d dt, or take the derivative with respect to time of our equation. That's going to be 2x times x prime plus 2y times y prime equals 2d times d prime. Now let's take a look at what we were given in the equation. We were given the fact that the truck was changing its position at 15 meters per second. That is a speed, that is a derivative, that is a rate of change. This is dx dt, or this is x prime. The 20 meters per second is the speed of the van, or how the van is changing its position. That is a y prime. So what we want to do now is we want to freeze our picture. Freeze our picture, there we go. And at the instant the truck is 60 meters west, the van is 80 meters north, and we want to know what this distance is. You can use the Pythagorean Theorem, and this works out to be 100, or a 3, 4, 5 triangle. So let's just plug and chug. We have 2 times x times x prime. How was the truck changing its position by 15 meters per second? So x prime, or the change of x, is 15 meters per second. By the way, that 60 was meters as well. Plus 2 times y, that was meters, times y prime. And the van was changing its position at 20 meters per second. So that's going to be 20 meters per second. And this equals 2 times d times d prime. Well, that doesn't look good. Now, d factorial, really, Mr. G? Am I yelling? We're going to extend this page and write this better. 2 times 60 meters times 15 meters per second plus 2 times 80 meters times 20 meters per second equals 2 times 100 times whatever the rate of change of that distance is, which is what we're looking for. All right, I'm going to go ahead and divide everything by 2. No reason to have that extra stuff there. And so we're going to get 60 times 15. 10 times 15 is 150 times 6, that's 900 square meters. And that's going to be per second, plus 1600 square meters per second equals 100. By the way, that 100 was meters. 100 meters times d prime. Extend my page. So I get 2500 square meters per second divided by 100 meters gives me my rate of change of my distance. Knock off 2 zeros. 25 meters per second is how that distance is changing between the truck and Martin Van Buren. So let's go see what we're going to circle. We go all the way up here and we circle E. Let's do another example. A balloon rises vertically at the rate of 10 feet per second. Vertically means straight up. Straight up, Mr. G. Not like to the left and slanted. Okay, sorry. Straight up at the rate of 10 feet per second. This is going to be y prime. That's how the y coordinate is changing. A person watches a balloon ascend from a point on the ground 100 feet away from the spot below the rising balloon. At what rate, radians per second, is the observer's eye rotating upward to follow the balloon when the balloon is 50 feet above the level of the observer's eye? So let's come down here and draw a picture in motion. I've got a balloon going straight up, and I've got this little person over here. We're going to have this little person right here, and their little eye, they're watching it rise. So they watch it rise, and then it goes up some more, and you can see that, back to my pen, you can see that the angle is increasing. So that's like your picture in motion. And again, we're going to have the Pythagorean theorem here. I've got a horizontal distance from the person to the balloon. The balloon is rising vertically, right angle. So, and then I again have x, y, and I'm going to use, I guess I'll stick with d, I might as well. X, y, and d. And I also have theta. Theta is increasing. What is happening to x? Is the value of x changing? Of course it's not. This person is not walking forward, so x is going to be what's called a static or a quiescent variable, which means it's unchanging. And that person is 100 feet away from that spot. So let's come down here and draw a better picture. Hopefully I'll do a better picture. So I drew my picture in motion. 100 feet away, the balloon is changing its position, so that's why, and the distance is obviously changing, and so is this angle. Alright, so you have to figure out what equation relates all of this stuff, but do we need to worry about the distance? Is the distance a part of the question? The distance between the observer and the balloon. Let's see, the balloon's going up, so that's changing. Person staying still. We want to know how the angle is changing. So that means we don't care about the distance between them at all. We just want to know what is happening to theta as y changes and 100 stays the same. So we can figure out an equation that relates theta, y, and 100. This is not really going to be Pythagorean theorem this time, is it? Because we don't need that distance. We need to, how are two sides of a triangle related to an angle? That's trigonometry. And we need to come up with an equation that relates the opposite side to the adjacent side from theta. And that equation is tangent. The tangent of theta is equal to y over 100. That is my equation. That's what I'm going to ddt. Now I want you to think about this as the tangent of theta equals 1/100th y. The 1 over 100 is simply a coefficient or a constant in front of the y. So what do we do next? Well, we ddt that equation. So let's extend our page. If we take the derivative with respect to time of tangent theta equals 1/100th y, what do we get? We're going to get secant squared of theta times theta prime equals 1 over 100 times y prime. This is the point at which we freeze our picture. So let's freeze our picture and see what's going on. We know this is 100, and we come back up here to the top, and we're supposed to freeze the picture whenever the balloon is 50 feet above the level of the observer's eye. Go on down. La la la. Okay, so here we go. So if this is 100 and this is 50 and this is theta, let's go ahead and see if we can plug things in. We want to find theta prime. What was y prime? I'm sorry to have to keep doing this. I've got to figure out what is y prime. That is 10 feet per second. So I do secant squared of theta times theta prime equals 10 over 100. So this is like Secant squared, by the way, is a reciprocal, a cosine. So let's figure out what the secant of this angle is, and then we'll square it and we'll figure out what's going on. So I need the hypotenuse to figure out the secant of this angle, because the secant of this angle is hypotenuse over adjacent. So I'm going to do 100 squared plus 50 squared equals, I guess I'll call that d squared. So I've got 10,000 plus 2,500 equals d squared. So 12,500 is d squared. That means that this distance is the square root of 12,500. Okay, so let's plug this in. What is the secant of the angle theta? Well, the secant of the angle theta is hypotenuse over adjacent. So what is secant squared? Well, secant squared is going to be 12,500 divided by 10,000. We can go ahead and knock off 2 zeros if we wanted to. And 125 over 100 can be divided by 25, and that's going to be 5/4. So we know that secant squared theta is 5/4. So 5/4 times theta prime equals 1/10. Multiply both sides by 4/5, and we get that theta prime is 4 over 50, which is 2/25 radians per second. That answer is la 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 right there. All right, so we have a worksheet to work on tomorrow in class, and I will see you then.